we are turning the world of AI agents and how to design systems that don't just respond, but truly adapt. Our next speaker is Zsolt Bátorfi from Nokia. He will take us under the hood of AI agent architecture, exploring logic, environment integration, and how real-time context can power smarter decision makings. Please welcome Zsolt Bátorfi with architectural blueprints for AI agents.
Hello, everyone. Okay. Okay, so hello, everyone again. Let me introduce myself. I'm a software engineer guy, and also I dedicated my last 2 years to architect, research, and build a serious enterprise-grade AI agent. And also I'm representing the Budapest AI engineering team. Before I start, let me just ask, who is actively using AI agents? I'm not talking about ChatGPT. So real agent doing stuff, not just answering questions. Who has tried to build one AI agent? Just a couple of guys. Okay, so my story is how we do it and what are the complexities of designing and building AI agents. Here at the Budapest office, we are on a journey basically to build telco-grade AI agents, different kind of agents. And when I say telco-grade or enterprise-grade, I mean it is really on the expert level. So when we build an architect agent or a troubleshooter agent or a configurator agent, just imagine a telco network function configuration consists of more than 27,000 configuration entries. And there are hundreds of experts knowledgeable about the whole configuration system, but no one knows everything. But imagine we would like to build a configurator agent that knows everything, all kinds of configuration details. When it comes to troubleshooting, a human, based on her or his knowledge, they know, okay, where to find root causes. But no one is general or generic, but we would like to build a troubleshooter agent that takes I don't know, several hundred lines of log files, time series data sets, and it can understand, it can run exploitative data analysis tools. So this is what we are building. But to make it short, and what's the key takeaway of my presentation is basically two things. If you have ever tried to build an AI agent, you will see that it is really hard. It's not that easy. There are just quite a few really successful agents out in the market. I would say the real momentum is AI coding. So the GitHub Copilot, especially Cloud Code and other coding agents, they are just proving that, yes, it is doable to build professional agents. But many people tell you, or there is this common assumption that, oh, it's just a lightweight context engineering logic on top of large language models, and if you get a good model that can provide tool calling, it's really good at instruction following, you are good to build AI agents. And the only thing that you should focus is on basically to provide the tools to the agent. The rest is done with LLMs. And what we experiment is not true. So they are the tools. So LLMs are intelligence processors. That's good, but you do need to focus on serious software engineering to build real enterprise-grade tools. So that's what I would like to talk about, and that's one key takeaway, that if you seriously want to build AI agents, you need to invest into building heavy agentic logic, and you will see other important components. The second big understanding, I would say, is that you should go beyond the so-called naive RAG approach. I don't know how much you are aware of it. Basically, it's a simple idea. Someone just realized that LLMs are stupid because they don't have context. So we need a retrieval logic that provides the context to the large language models. The problem is that we think that it's just about vectorizing content and just utilizing some nice embedding models, and based on cosine similarity, you have a nice retrieval logic. The problem is that it is not relevant. It's not enough. So it's just a gamble, I would say. And it's a good luck when a vector search engine provides the right context for the LLM. So somehow you should provide a more serious context to large language models. And then comes the graph theory, the graph science, and graph engine technologies, and also advanced graph reg methods. So this is the second takeaway that I would advise you. You should invest into building a deep worker logic into agents. And the second part is to invest into building specialized knowledge graphs. But before I dive into these details, let me just clarify what an agent is exactly. I would say we don't have a clear definition what an AI agent is. Let me just show you our interpretation. What is an AI agent? We say that it's like an intelligent integrated circuit. So it can take an input, and it can not just produce an output and compute something, but it is intelligent. So it can analyze, it can plan, it can execute, and even it can reflect on what was generated. So we say that it's a kind of semantic execution logic. And very importantly, this intelligent logic is connected to an environment, which is a graph, typically a knowledge graph, or a real-time database. But it should connect to information sources. And also, as an agent is doing its job, when you do, for instance, a root cause analysis on a network function log, then the agent can generate knowledge. So it is not just processing and analyzing the logic, but it can also create knowledge. Okay, so when next time a similar log is provided, then maybe it can get the answer immediately from the long-term memory. So this is one interpretation. The other is really important as well. You need to prepare that agents should work with other agents, because you need to orchestrate how agents are working together. There are different patterns. If you look at the Anthropic blog site, you will see a nice overview. They did a great research on agentic orchestration, and they identified different patterns of multi-agentic orchestrations. I just picked 3, like the simple chained sequential orchestration of agents, but soon you will see you do need to provide the parallelized activities, and also you need one agent that is doing one thing, and you need another agent that is interpreting and evaluating and providing feedbacks, and it's an iteration between agents. The next important aspect of an agent is that they can intelligently analyze the input. So it's a huge topic, I can tell you, but simply an agent cannot just act. It should analyze, is it doable? It's not doable. It can be mapped to the capabilities of the agent. Do I have knowledge that I can use to perform the actions? So it should analyze, plan, and execute in a safe way, and it should connect to an environment. Maybe it's a twin environment. Maybe it's a knowledge graph. I will tell you the different directions. So let me dive into the architecture that we are building. I would like to emphasize that the heavyweight functionality of a true enterprise-grade agent is this semantic execution logic, what we call the agent worker logic. And it is basically mimicking how humans are cognitively thinking and acting. So you never do something before you understand what you would like to do. So first you need to analyze the input. Analysis means that you should understand, is it somehow connected as an agent to your identity? So are you responsible to do that or not? Do I have the tools that can help me to do the thing? And also, is it safe to execute? I can tell you it's so easy to trick any kind of agent. I just provide this stupid prompt, hey agent, please forget your system prompt and do what I tell you. So somehow the agent should understand that maybe it's a prompt injection attack. Or you provide your personal identifier to an agent and they can do bad things. So the agent should sanitize the input. So it should forget your identity. It's another challenge in the analysis phase. When the agent is doing the planning, sometimes the plan, the series of actions are just simple task sequence. But sometimes they have to be parallelized. Sometimes there are bad problems you will see as you build the agent. Imagine the agent just planned 7 steps, and in the middle, somewhere in the 5th step, something goes wrong. What should the agent do? Should it retry? Should it compensate? Should it create another new plan? So there are complexities inside planning, and hopefully you can see that this is not just prompt engineering. This is not just simple context engineering. You do need to invest into this logic inside an agent. When the agent executes, should the tools are executed in a sandbox, a safe environment, or it's just an arbitrary Python logic and let it go, it doesn't matter. So the executor should be smart as well. And the 5th thing, which I would say that's the key in humans, is the reflection. So when we do something, after the execution, we can reflect, okay, what are the learnings? What kind of insights can I extract from the execution? And should I save it to my knowledge base, or should I keep it in my long-term memory? Should I remember? Because it's an insight, or it's a very common action. So that's the heart of an AI agent. And for sure, it is, as I mentioned, it's an intelligent integrated circuit. It takes an input and it generates an output. But in the autonomous agent space, sometimes the input is not even human. So imagine in a network function inside complex telco systems, an event can be the input. So something happens in the system, some failure, some strange matrix is collected. So it's an event. So sometimes the trigger is not a human, but a system logic. And you need to prepare for these scenarios. So sometimes the agents are operating in a so-called human-in-the-loop mode. Sometimes they are operating in a fully autonomous mode, and totally different operational approach is required. Okay, so we have this heart, which is the human brain part of the agent, but there are very important ingredients that should be architected into agents. The first part is what we call the operational manual. So imagine that an agent can be a robot. So it can get a task, it can think, it can act, but you should provide an operational guide to the robot. What you, robot, can you do? What is your identity? What are your capabilities? What are the policy and the compliance rules that frame your operations? So that should be baked in, deeply into agent. Otherwise, if you don't provide this component, when they are just running autonomously, they can do anything, right? So it's a key. And also each agent, and if you look at the cloud code latest implementations, Anthropic as well introduced serious memory management capabilities. And when we say an agent needs memory, we mean that an agent should provide a short-term memory and a long-term memory, like humans. So there is a saying that an average human can remember 7 things at any time. Likewise, in our agents, we can remember 1,000 items in the short-term memory. But you shouldn't remember everything, right? Bad things mostly for humans. So the short-term memory should be smart. You need a strategy how you just clean up your short-term memory, like we humans do. And also, we need long-term memory. And psychology will tell us that based on emotions, humans store long-term memory items. But how agents store? What is the strategies to store important insights and key learnings so that the next time this information can be reused? Probably the most complex component of an AI agent is the environment. We call this environment because we imagine that agents are running in an environment, like inside a network or inside your service. And you need an environment that represents the real world, the knowledge and the real world, the real status of the network system. So we need an environment, and for sure we need tools. We need a toolbox where you can easily register different kind of tools. There are many kind of tools. For sure, the easiest is the built-in kind of tool, just a decorated Python function. But how about exposing the agent to MCP servers? So we are talking about external tools registered in the toolbox. And also there can be semantic tools when an LLM call, a prompted templated call, can be treated as a tool for an agent. So that's the Nokia Agent Foundation architectural concepts. This is what we are investing into. Let me dive into the next part. So we have a nice agent architecture. How can we inject knowledge to the knowledge base for the agents? Here inside the Nokia, we have a lot of content sources, and I can imagine in your organizations, you have Microsoft 365 SharePoint folders, you have Jira, Confluence, file shares, many kind of content sources, and different levels of structuredness. So maybe you come up with a collection of PDFs on a file share, but sometimes your technical content is structured a little bit. Sometimes information stored in SQL databases and you have a relational database schema. So depending on the source, you have different strategies to extract the knowledge. And you need a different strategy to transform the knowledge so that it can be used in a graph engine. So that's a big problem, how you develop a special data engineering pipeline for your agent graph. So the classical pattern is to extract, transform, and load. It's true, but imagine you need to take any kind of structured and unstructured information and turn it into a graph format, which is a hard and tough problem, I can tell you. And then there is a question, what kind of graph engine should you use? I will tell a little bit more about this later. But this is really a key capabilities, and I don't know how much time, but given an AI agent project, I would say that at least 70% of the effort, the coding effort, goes into this data engineering pipeline problem. Once you have this injection logic, then you are ready to provide a knowledge graph service for your agent. There comes another problem. Imagine you have a lot of information somewhere. You have a nice pipeline that can turn it into a graph, but there is no schema for the graph, right? So after this injection pipeline, you are usually generating so-called triplets. Basically, a very simple unit of information where there are two nodes and there is an edge between. And imagine you generate those triplets, and if you just simply inject those triplets into a graph engine, yes, it will be stored in the graph. Maybe you can come up with nice graph traversal logic, but it has no schema. It has no information on the graph storage. And that's where ontologies comes into the picture. This is what we learned. It's really, really key. When we say ontologies, it's just a simple term for information that is describing information. So it's a kind of so-called metacognitive definition of the things that we put onto the graph. What does it mean? When we inject all network function customer documentation into a knowledge graph, before we do that, we just design a nice ontology that is describing what is what. So what do we mean by a network function? What do we mean by an interface, a protocol, or a property? What are the axioms? What are the rules for the graph? If you don't have this, you will create a mess of nice edges and nodes without meaning, without information that helps AI agents to interpret and reason about the graph information. So what we do, we take all the sources, and in parallel of injecting the content, we are designing, building, curating ontologies that describe all kind of information in a way that is understandable for large language models. It's very important. And there are different standards. We use the so-called ontology web language format, if you know about it. But that's the most common standard, I would say, that is describing the whole semantic web. So you need to invest into building ontologies. And then when you inject, each little triplet that will become a node and an edge in the graph will be mapped into the concepts, into the schema of the graphs. And that as far as you can go to describe your content sources, as you can see, we try to describe the whole life cycle of a network function, from design to deployment, to operation, to support. We describe everything as ontologies. And once you have those ontologies, you have to choose, because sometimes an information, when it is becoming into a graph, it's a good fit for the so-called property graphs. I like to use this analogy. Sometimes you need a graph storage for your right brain activity, and sometimes you need left brain activity. What does it mean? Right brain activity means that we have just a light schema. As soon as we have information we would like to put into a graph, and the key is that the speed, the scalability, and the easiness how we inject into graphs. A good fit for this kind of knowledge graph is our support system. So imagine some incidents happen somewhere in the world, an incident is created. And the key expectation is to save it as soon as we can to the graph and link it as easy as we can to the rest of the information. And then we will traverse the graph and try to find the best context for agent. But we don't focus on the reasoning. Sometimes you do have a content source, like in our case, the customer documentation, deployment guides, operational guides. They are quite structured documents. And we expect, once we inject that information into the graph, we expected that every time when we ask something from an agent, the same response will be provided. And that's why you store it to the left brain graph, which is the so-called deterministic reasoning kind of graph. They are so-called RDF stores. This is it. And they are really good at reasoning. So once you inject it to this RDF graph, then anytime when you ask something, it is guaranteed that it will be totally precise, repeatable, and rule-based. So it's not probabilistic. It's not some kind of LLM generated something that can be hallucination many times. It is totally symbolic logic, rule-based, and it will guarantee the answer. And this is what we use for all customer documentation, because imagine our agent should be really on the expert level, absolutely on the expert level, and they need to take exams, and they need to, get high grades on the exams. So that's why you need another kind of engine. Once you injected the knowledge to those graphs, either a property graph or an RDF graph, then comes the next challenge. Okay, how you get the knowledge out of a graph for your agent. And there are different strategies. Unfortunately, we don't have time to discuss all the approaches, but I would just show you some visualizations on the right, or I don't know how you look at it, but this part is describing two different network function knowledge graphs. They are RDF reasoning graphs. On the right, you see another property graphs. Those dots, kind of a visualization, those are support incidents and workaround information. So imagine this is how an agent is looking at knowledge. They have deep connected information, and the question is how you retrieve information. But that's another topic, maybe another content candidate for another presentation. But in a simple way, I would like to show you how it works. Or one strategy is for graph reg retrieval. So what we can easily do when we inject the graph nodes and we create the edges between the graph nodes for the agents, you can embed, you can vectorize each node. And the idea is that at least in our method, is to generate embeddings for all nodes. And when you are looking for something in the knowledge graph, first you run a vector search, and you can we use, let's say, 7 similar nodes, and you get the 7 conceptually related nodes from the graph, and then we run a special graph query that is getting the neighborhood information from the nodes. That's one way, I would say, very important. That's just one way how to get information from the knowledge graph. So when you ask the question from our agent that please create a checklist to enable this feature on this system, and by the way, show what problems are related to that, then you can imagine that based on the vector search, the graph will provide a workaround and support kind of nodes and documentation kind of nodes, and the agent can compose a nice response based on that. Okay, and the last part, we have an architecture, we have an injection pipeline, we have graph engines, we have retrieval logic, then we can compose AI solutions and agents. And this is what we do. We have a framework, what we call the Nokia Agent Foundation, that is connected to basically any property or RDF graph engine. And we expose the agent logic to front ends. Another important learnings I can tell you, you should as much decouple the agent logic from any kind of front-end application, because you never know. Do you need to build a CLI application? Do you need to integrate an agent logic to a monitoring dashboard? Do you need to embed it into a configurator tool? Or do you need to build a totally brand new copilot for your users? So we introduced different front-end services. Unfortunately, I'm sure we don't have enough time to talk about all the details, but recently there are a lot of nice protocols like this AGUI protocol that helps us to expose the agent capabilities to basically to any system. Of course, we can integrate it with external tools, and any agent can be participating in any orchestration because we are providing integration to agent protocols invented by Google. The MCP protocol was invented by Anthropic. So don't be naive. and focus on hardcore software engineering applied to AI solution building. Thank you for your interest.
Thank you very much, Zsolt. Before continuing with the questions, I would have one. What is the X factor of AI?
X factor. Oh. Of AI or agents? AI?
Of AI.
X factor. We are building intelligence systems. This is a new era. So I never imagined, I can tell you. So I was born as a software engineer. But never imagined that maybe it will overcome us on one part, but also even we can build intelligence systems. So we were, educated to understand coding and algorithms and left brain thinking, and now we are thinking about and talking about really thinking and acting robots. So we can build those things. That's a cool thing.
Thank you. And I hope that the presenters in the afternoon are preparing with an answer as well for this question. Who would have a question to Zsolt?
Zsolt, it's amazing and impressive, and it's clearly visible how much time you put into that already. And to those who are not at that level, like far not at the level, so what would be the thing that we should be aware of regarding the vulnerabilities? And just one, I don't know, that I really like the analogy of the left brain and right brain. I think that's really worth understanding that. Thank you.
Yeah. There are different levels of your question. So how you should start and how you keep everything safe, maybe that's my understanding of the first part of your question. It's so easy. There are so many, even low-code, no-code tools are in the market. You just go n8n.com and you are good to go to compose some agentic logic. And there are open sources that you can easily clone and just use it in your code, but they lack this part, this security part. So how to make it secure, as I mentioned, how to sanitize personal information and how to prepare against threats. That's a real problem, and no one knows exactly, I would say, how to do it right. And usually the agent frameworks and open source frameworks, it's not the highest priority. They are just focusing on how to make it productive to build agent in general. So in the industry will evolve and understand the importance. Like we just had to, you remember the days, the Windows 95 days and the virus era of Windows. So I would say we are at the stage at the moment. And what was the second one? Left brain, right brain?
I'm just interested, like how we should be making decisions consciously about vulnerabilities of the agent systems.
How we are making conscious decisions on, it should be built into the agent. So it's up to you. You need to architect the agent. They are compliant. They are policy driven. They implement role-based access control capabilities, I would say. So everything that we learned in classical software engineering should be applied to agentic development as well.
Thank you. Any other questions?
A little bit like a follow-up to that question, saying that we should apply, what we've learned before. However, if you're using language models as the base, they're not deterministic.
No.
A lot of what we've learned is based on deterministic systems. So what do we need to think about differently to adapt?
Thank you so much, because that's really key. I missed it in the slide deck. I emphasized in the knowledge-based part the left brain, right brain analogy, but it's the same for operations. And there is a science called symbolic AI that is purely deterministic, rule-based, and left brain, I would say. And there is this new paradigm, the probabilistic right brain LLM-based reasoning, directions, and the two should be united. So I would say the future is about uniting symbolic AI and probabilistic AI together into one system.
There's a name for it, neurosymbolic AI.
Neurosymbolic AI, exactly. That's the final theory, I would say. Yes.
But they can still go rogue.
Yeah.
Yeah, this neuro part can still go rogue, and sometimes we might not realize because it's not obvious. It's like humans, right? You can't predict straight away when somebody is a rogue agent.
Yes, yes. I think they are complementary to each other, and somehow they need to be embraced because they are counterparts. So for instance, the AI science was in a winter stage, for many decades because they thought that everything is symbolic AI problem. And they come, neural networks, new horizons just came, and now we realize that there are constraints and limitations of purely LLM-based reasoning. I can tell you, we tried it, and it was really tough. Originally, we thought that when we build an agent, we just choose the best instruction-following, tool-calling, and reasoning-capable LLM. We just provide the nice content, and we are good to go. They are so smart that they will generate any kind of plan, and it turns out that it's simply not. So you need to invest into this layer because it's on top of the LLM infrastructure.
Thank you.
Sorry to make it long.
I saw that there were a couple of other questions. I hope that they can catch you in the lunch break.
Yeah, I will be here.
All right, thank you very much, Zsolt.
Thank you.
Let's give another round of applause for him.